All right, recording's already started. All right, we're looking at chapter 7 puzzles. All right, so we did all the rotational ones and some of the gravitational. We got these three left. We got these three left to do. So number 44. 44 is a three-parter, I think. 600 kilogram satellite in circular orbit around Earth at a height above Earth equal to Earth's mean radius. Interesting. Find the satellite orbital speed, the period of revolution, and the gravitational force acting on it. All right, so let's check this out. Number 44. Right, so here could be Earth. Maybe has some mass and some radius. Right, they did say orbiting. Yeah, orbiting Earth. Right. Right. So maybe we might be allowed to know what is the mass and the radius of Earth. Right. There's some satellite here. It's in a circular type orbit. Okay, and its distance is 1 Earth radius above the surface of Earth, right? So you could say the distance from the center of Earth to that satellite is effectively 2r, isn't it? 2 times the radius of Earth. Okay, so maybe that'll be helpful. Okay. Now, low Earth orbit. Did I solve a low Earth orbit with you guys before? Do you guys know how much time it takes, like, International Space Station to go around Earth? It's about 90 minutes, about 90 minutes, right? So that's low Earth orbit. This is not low Earth orbit here. This is like way further than that. Right? There is okay. Side note, my other students got a textbook question that said something about a geosynchronous orbit. Do you guys know what geosynchronous is? Yeah.
Orbit period is same as the rotational period.
Exactly. Yeah. That would be like somewhere way out here, where it would take 24 hours for the satellite to revolve around Earth, which would match Earth's rotation. So from the point of view of Earth, it looks like it's in the same point in the sky all day, every day. Right? Okay. That's also not what this is. I just wanted to side mention that so you can think, that's an interesting scenario, right? It would be a really useful place to park a bunch of satellites up there. Right. But this is saying, question A, what's the satellite's orbital speed? Okay, so supposed to give it like an orbital speed right there, like a tangential speed. How fast is that? Right. Can you guys, so challenge question here. Can you guys solve orbital speed from scratch? Let's do a pop quiz in your notes. Pop quiz. Here, go ahead. Derive orbital speed from scratch and take a quick walk around the room. Derive orbital speed from scratch. There's an expression for it. There's like 3 steps to get to it. Let's make believe that you guys are solving an FRQ right now, and they say something really similar to this, and you got to solve orbital speed from scratch. This might be like 3 points by some AP graders rubric. Might be like step 1, 2, 3. They got 3 points lined up, and if you can derive orbital speed from scratch, should be something you should be able to do. Okay. So that's this poster right here. Here's the answer. Here's the answer. Okay. So you say there's only one force on it, which is gravitational force, and that's acting as the centripetal force. Centripetal force provided by gravitational force. Centripetal force. Here's the answer to one of your recent labs: mv squared over r. The Plato canister as well. Okay. And here's Newtonian universal law of gravitation. Right? The mass of the satellite itself cancels out, and then if you solve for this v, here's orbital speed for a circular orbit. Right? You guys remember this? Okay. You should be able to do this. Look, 1, 2, 3, 3 steps. You guess that? Can you guys see that? Yeah. So let me just cut straight to that. So we got orbital speed equals square root gm on r, where universal gravity constant, mass of whatever's being orbited, in this case, the planet, right? And r is the radial distance from the center, right? Just in this case, 2 times the radius of Earth. Right? So let's plug in some numbers here. Right. Let's say you're allowed to know what these numbers are. I'm just going to go ahead and fill them in. So g is 6.67 times 10 to the negative 11. That's meters squared per kilogram squared. Mass of Earth is like, I'm going to call it 5.98 times 10 to the 24 kilograms. See different textbooks use slightly different values. I'm just going to pick one and go with it. Right. And then, now this r is actually 2 times the radius of Earth, isn't it? Right. So maybe I'll write that as a side note here. R in this context is 2 times the radius of the Earth. Right. It's very big. So I'm going to do 2 times 6.38 times 10 to the 6 meters. Right. That's all right there, right? Right. All right, so let's do calculator practice. You guys pull out your calculators. Let's put this all in the calculator and figure out what's the orbital speed. Okay. Now, does AP ever want you to like do big calculations like this? That tends to not be their focus. I doubt they would ask exactly this question. But you should be able to do this, right? And this is good calculator practice to be able to navigate. We got scientific notation, we got fractions, we got radical going on, right? So I'll do square root. Open up excess of parentheses just to make sure everything's grouped in there. 6.67 times 10 to the negative 11, 5.98 times 10 to the 24, and then divide by, and then I got a bunch of stuff down here in the denominator. I want to make sure it's all grouped in the denominator. 2 times 6.38 times 10 to the 6th. Okay. Now this model calculator will close all my excess parentheses for me. Not all calculators do that, so we're that. Okay. So give you guys time to, before I hit enter. Okay. So what does AP care about? AP usually cares about like proportional type questions. So they might say like, what if you have like different satellites orbiting the planet at different radial locations? What's the ratio of their speeds or something like that? That's more of an AP one type question. Here's another thing before I hit enter is let's come up with a guess, like a reasonable guess, so that when we see the number, we say, okay, yeah, it's kind of in the ballpark of what I was thinking to begin with. Okay? Does anybody remember? Let's go back to low Earth orbit, like way down here, low Earth orbit. How fast do you have to go near the surface of Earth to orbit the Earth? Does anybody remember that? I think we ran a number the other day. It was about 7,900 meters per second. Sometimes you hear like 8,000 meters per second. 8,000 meters per second. Okay. So if you're getting further and further away, do you think you have to maybe not go as fast? Okay. In fact, we've got the relationship right here. It's like 1 over the root. Right? So there's a proportional kind of question right there, right? Like if you effectively double the distance away from being like what a low Earth orbit is, right? We've got a factor 2 down here. Right? The square root of that is like 1.4, and we're dividing by that. So let's take 8,000 divided by 1.4. You think what, about 5,000 or 6,000, somewhere there, meters per second? I bet the number on my screen is going to show about 5,000 or 6,000 meters per second. You guys think? Right? You could get that from proportionality, which again would be like right in line with what AP actually would ask. Okay? Let's see. Let's see. Oh, look at theirs is 5,591 meters per second. That is about 5,000 or 6,000 meters per second. And it's just right in there, isn't it? Okay, there you go. Okay. And that was question A. Question B. What's the time period of revolution? Okay. I can think of at least 2 different ways to get the time period. Somebody tell me, what's one way you can get time period? What's one way? What's one way you can get the time period? Like how much time does this take to go around the Earth? Right? I mean, just kind of eyeballing it. I'm pretty sure this is less than geosynchronous, so it's going to be probably less than 24 hours, but definitely more than 90 minutes because it's kind of far out there. So more than 90 minutes, less than 24 hours. What's one way you can solve for how much time? Okay, maybe something kind of kinematic sort of, right? Maybe like distance equals speed times time. Ooh, the distance around. Would that be like the circumference of a circle? Right? You know what? I'm kind of remembering back when I had you guys do your labs, when you had the Play-Doh canisters and the string and you're wheeling around a circle, I had you guys calculate the speed. And the way you guys did it was you said, well, the speed it's going, I'll call it orbital speed, but it's like a tangential, right? Is you guys did the circumference, which I'll just go ahead and call 2 pi r, divided by the time period that it took to go around once, right? Wouldn't that be that? Now, in this case, we're solving for t. Oh, maybe I should rearrange this and go like the time period then is going to be 2 pi r divided by the speed. Isn't that what that would be? Right? Here's your lab version, just algebra rearrangement. Here's how much time it would take, distance over speed. Right? One of the first questions I asked you in this class, I said, if you're driving towards Jacksonville, suppose you see a road sign that says Jacksonville is 140 miles away. You look at a speedometer, I'm going 70 miles an hour. How long does it take to get there? 140 over 70. Is that 2 hours? That's the same thing right there. Right? So, because we got the speed, because pop that down there. Right? Now, keep in mind this this little r is actually 2 times the radius of Earth. Right? So remember that right too, right? So let's put that all together. Time period is 2 pi times, and then for the radial location, I'll go 2 times the radius of Earth divided by the orbital speed at that location. Right? And then we'll plug in some numbers. Yeah, good calculator type practice right here. Right, 2 times 6.38 times 10 to the 6 meters. Right there. Okay. And we came up with 5591 meters per second it's going at. Right. Right. So while you guys are writing that down, punch that in your calculator. Let's think ahead a little bit to what we're about to see. This number we're about to get, what units is this number going to have? Seconds. Ooh, you guys think it takes a lot of seconds to revolve all around the Earth, right? Yeah, I'm thinking so. So, okay, yep, we're definitely getting a big number. 3, 40, about seconds, right? Do you guys think it might be reasonable to maybe convert that to, oh, I don't know, hours maybe? Hours? Right. Kind of go maybe 60 times 60, is that 3,600 seconds and 1 hour? Like that. Okay. So yeah, that looks like a maybe easy way for brains to crunch, right? Over 3,600. Okay, I'm getting 3.98 is the number, and hours is the unit. So you might even just call that 4 hours, right? 4 hours takes 4 hours. Ooh, that's interesting. Okay. So I could think of at least another way to do this. Okay. You guys remember Kepler's third law tells you something about the relationship between how much time to go around and where it is, right? Yeah, you guys remember this? Okay. Now Kepler just figured out this proportion. If you bring in Newtonian mechanics, you can make an exact equation out of this. You guys remember that? Let's apply this equation. Hey, I wonder if this will also tell us 4 hours. Let's do that. I'm just going to copy paste this right here. Okay, do that. But let's solve this a different way. Okay. Time period is 2 pi times the square root of the distance to the power of 3 divided by gm. Right? I mean, really, it's just a different perspective. I think we did prove this in class, like derive this. Right. Might be a while back in your notes. Okay. So time period is, I got a 2 pi times root. Okay. And remember, this r is actually 2 times the radius of Earth, so just keep that in mind. Okay. So we're going to go 2 times, and then 6.38 times 10 to the 6 meters. Okay. Now that's all being cubed. Right, then divide by, I got 6.67 times 10 to the negative 11 meters squared per kilogram squared. And then the mass of Earth is, I'm going to use 5.98 times 10 to the 24. That's kilograms. Okay. I keep this all grouped together in the denominator. This is all underneath this radical. Okay. So a few little details real quick. This is okay. Do you guys see how my square root bar covers like the entire fraction, and it extends like height-wise and lengthwise over that entire inside expression? I guess that I've seen many times, like over the years, even recently, like students like square root it, but the square root only covers the numerator, and it's like, is the denominator square root? What? Right? Or sometimes they'll like stop the square root like right here and say, wait, what exactly is being square rooted? Like if I just do a square root that's like up here in this corner, it's like, okay, I'm trying to communicate to whoever's looking at this that I'm square rooting this entire inside expression. Okay, guess it. Okay, so all right, let's plug the numbers in. So 2 pi times, and then a square root, and excess of parentheses, 2 times 6.38 times 10 to the 6, because 2 Earth radii is where that comes from. Okay, close that to the power of 3, then divide by, then open up some excess of parentheses, 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24. Okay, so I'm getting 14,340, that's seconds, multiplied by 1 hour every 3,600 seconds. That is, oh, look at there, 3.98 hours. It's the same thing. Okay, there you go. So we're going to be able to navigate questions like that. Oh, there is one more part. It says, what's the gravitational force on it? And if you want to know gravitational force, you have to know the mass of the satellite. Actually, they do give you the mass of the satellite. I just haven't used it yet because it's canceled out so far. So 44 part C, weight, or F sub G, if you like, is, how about, well, wait, how to do this? Okay, never mind. Let's do G M over R squared. You could do, right? Maybe there's different ways you could do this, right? But you could just plug in the numbers, right? Okay. So, I know what I was thinking, right? But let's do this, right? I was thinking I had a shortcut in mind. I just remember what my shortcut was. Let's go back to this. N times G, right? N times G. Okay. So let's do my shortcut trick here, which is remember where this satellite is like proportional to the radius of Earth. It's one Earth radius above the surface of Earth. That's where the satellite is. Okay. So if the satellite was down on the surface and it had a mass of 600 kilograms, it would weigh 6,000 newtons. Okay? And up here in orbit, it's effectively twice as far away, which means that it's going to have what proportion of its original weight? 1/4, right? Because factor 2 here, 2 squared is 4, it's 1 over that, 1/4, right? So if it has a weight of 6,000 newtons down here, so it shouldn't be 1/4 of that up here. Or let's do it in terms of gravity field. Gravity field at surface, is that 10 meters per second squared? What is the gravity field way up here? 2.5 meters per second squared, right? It's 1/4. So we got 600 kilogram mass at 2.5 meters per second squared. There you go. So whatever that is, 600 times 2.5. Yeah, so 1,500 newtons, because we're talking about a force. Okay. You guys get there? Okay. Number 56, show that the escape speed from the surface of a planet is directly proportional to the radius of the planet. Right. Now, escape speed, we can actually prove this when we get to conservation of energy, which we haven't quite, but I have shown you guys this expression here. So we're going to play off this. You see this? I'm just going to copy this. Right, so maybe you have like a small planet, and a medium planet, and a big planet, right? And we're trying to like blast off a rocket at some speed so we can cut off the engines and still escape from it. Okay? Do you guys think you have to go faster and faster, faster the larger planet you get? Right? Right. Now, supposedly what they're saying, their claim is that it's directly proportional to this radial size. So as the radius gets bigger, 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 right? Like if it's 3 times as big, it should be 3 times the blast speed. Okay? This equation, at a glance, it looks like it's saying the opposite. Because look at that, it looks like it's somehow inversely proportional to the radius. But don't forget that this mass here is not independent of the radius itself. Right? Like if all these planets have the same density, if they're all made out of the same material, the mass is also increasing with the radial size. And that is actually, go a little bit fast, has a cubic relationship, doesn't it? Because mass occupies volume. So guys, if it's 3 times the radial size in 3 dimensions, that's 27 times the volume, therefore 27 times the mass. Don't forget that too. We're going to do a substitution right here. Do a substitution is what we're about to do. So escape speed is, so I got a square root, I got a 2, a g. Instead of mass, isn't mass density times volume? So I got density times, and then volume. 4/3 pi will take care of a sphere. And then r cubed is what I need right there. Right? And then divide by r down here. Right? Now, even if you didn't know the 4/3 pi to turn a cube into a sphere, the important part is that mass is proportional to r cubed. That's the important part. Now, do you guys see that one of these r's is going to cancel? So escape speed. Okay, so now we're getting real close to the answer. So I got a square root, I got a 2, I got a g, I got a density, I got a 4/3 pi. Those are all constants. Then I have an r squared, which is still underside the radical. Guys, what's the square root of r squared? R, right? So then I got all these constants, square root 2g rho 4/3 pi, whatever. Right? That's all constant. Then r. Therefore, escape speed is in fact directly proportional to r. So if you have a planet with 3 times the radial size, it's way more massive. It's like 27 times the mass, but you're also further from the center, right? And overall, you do need greater escape speed, but 3 times the radius is 3 times the escape speed. Okay. Okay, and we got one more. Right, number 75. There's this amusement park ride. Here's the premise: is that it's rotating, and the floor drops out, and this person is held only by some coefficient of friction. And the question is, what's the minimum coefficient of friction to hold them in this amusement park ride? Okay. Right, so this is rotating at some given omega, some angular velocity. So they did tell you omega in radians per second. let's do a free body diagram on this person right here. Right? This is gonna be a kind of a funny looking free body diagram. Right? I'm thinking of a few forces on this guy. This guy has a weight acting down. Wouldn't that be mg? Right? Which way does the normal force point? Towards the inside. There's your normal force. Right? And then the friction force acts this way. Wouldn't that be true? Right? And do you guys think friction force is equal to coefficient of friction times the normal force? Here, just to fit this in before the bell, I got less than a minute here. I'm going to show you guys my pre-solved version of this. Here, it's right here. It's right here. Okay, here's the solutions that you guys have in Google Classroom. Right? So friction force is here's same free body diagram. Okay, so we just did. Friction force is coefficient of friction times normal force. Friction force is equivalent to mg because the sum of the forces vertically goes to 0. And normal force, I can call that m omega squared r. Right? M is the mass of the person, that cancels out. So here's the coefficient of friction, like the minimum coefficient of friction you have to have. It ends up being this expression right here. Then you can just plug in whatever numbers you like. Okay. All right, and that'll do it. Right, that is a wrap on those puzzles. All right, just in time. Look at there. Here's the bell. Right, you guys have a great afternoon. I'll get board physics adventures for tomorrow. Yeah.